Good afternoon, everyone. Welcome to the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IAC. It's my pleasure to introduce today's speaker, Professor Vijay Subramanian. He'll be speaking on cooperative multi-agent constraint POMDPs, strong duality, and structural equivalences. Professor Vijay is a professor in EC division of the ECS department at the University of Michigan, Ann Arbor. He received his PhD in electrical engineering from the University at Illinois at Urbana-Champaign. His current research interests are in stochastic analysis, random graphs, multi-agent systems, and game theory, with applications to social and economic networks. Over to you, Professor.
Thank you very much, and thank you, Parimal, for the invitation and hosting me, and Rajesh as well. One thing I didn't add there was I have an alumnus of this department as well as a master's year many years ago. And the campus seems to look very similar, which is great. And there, yeah, some people I interacted with are coming, like Joy. And, I should also, before I talk, I should also acknowledge Anurag. I think he was one of the, very inspirational as an instructor and as a, coming from undergrad to see what you could do as research. It was very helpful, and so I have to acknowledge his inspiration and support through the years. So I'm going to talk about cooperative multi-agent constraint POMDPs. Most of it is actually going to be joint work with my now graduated student, Nouman Khan, who's at Amazon. So I'm listing some of the works, and still some of it is from his PhD thesis. Very briefly, I'll talk about another past student's work also. I don't think he works at JP Morgan anymore, but I don't know where he is. So I'll start with some acknowledgements. So yes, the first is, that's okay. So this is Nouman, whose work I'm going to talk about most of the time. Went off again. Did it? Oh, now it's coming again. This is Sue, who's the other student, whose work I'll mention only briefly. So some of this whole topic on multi-agent systems, I actually started working with another former student of mine, Dengwan Tang. We did mostly dynamic games there, and then this Teams thing came out of a follow-up of that. So I have to acknowledge his efforts in getting me up to speed on all these very conceptual topics. Another person I would like to acknowledge is Aditya Mahajan. I think he was here to give a tutorial. He has been my consultant in a lot of these topics. He's very knowledgeable and very helpful. I should also acknowledge my now retired colleague, Dimos Teneketsis, whose fingerprints are everywhere on these topics. Finally, I'll acknowledge support from NSF and ONR for supporting this research. Okay, so the talk is centered around decision-making in multi-agent systems and networks. So what are multi-agent systems? I mean, most of you are probably working in specific examples here, so I won't belabor the point. But essentially, the group of agents, they're decision makers who interact with each other in some sort of shared environment. I have some examples here. I'm not going to be focusing on a particular example, but more on the abstraction. So they're present in many varieties and forms in diverse applications. There are two extreme possible configurations. One is a cooperative setup, which is called a team. So there's a common goal. Someone has assembled a team. They're going to work as a team. They're not going to split off and do something on their own. This goes back to some work from economists Marshak and Radner in the 70s. And there's a fair amount of work on that. And the talk will be sort of focused on that part. The other sort of extreme is the competitive setup, where every agent is on their own. They have their own individual goals. And so I could have put Morgenstern and von Neumann Morgenstern, but I just put Fudenberg-Tirol there. But so where I'm going to focus on is common goals, but individual goals is the other extreme. But there can be things in the middle where you have games of teams and other configurations. In all of these problems, there are lots of challenges, and the challenges emerge from a few things. One is multi-agent interactions. There are different decisions being made, sometimes with some allied objectives, sometimes with conflicting objectives. So that's obviously one issue in the statement itself. The second one is what is more complex, is also complex information structures. Who knows what, when, and who knows the decision is taken, why are they taking decisions. And typically in these systems you have information asymmetry, that is, you may not know why I'm taking certain decisions because I have certain measurements that you don't get to see. And partial observability, I may not even see my own system very clearly. And so these are inherent challenges to these problems. An additional thing that I will add here is adding joint constraints. So there may be something that applies to more than one controller together. So this is the focus of the talk. It's a cooperative setting of a team with joint constraints, and I want to see how you would think of solving these problems. So before I get into the meat of it, I'll go with some background. So there's going to be a lot more I would say this talk is more conceptual than necessarily. So this is on sequential decision making and on information states is where I'm going to start with. So in any decision-making problem, you're taking decisions over time, so information increases over time. Typically, you get more measurements of whatever you've taken decisions as well. Those are part of your measurements. So this is usually what's denoted as history. I'm going to put it as private history. If you only get to see it, no one else gets to see it. Okay. This is it increases complexity and memory. I mean, even if it's finite size, it's going to keep increasing over time. And what is typically done is, of course, that makes things very hard. So you normally think of some sort of compression of that information into some sort of sufficient state, statistic. And in the decision-making context, this is called an information state. So this is a compression of history that is sufficient for decisions. As in, I am throwing out information, but this particular information state still allows me to take optimal decisions and I don't lose anything in that sense. It may do more than that. In some cases, it also is without loss of generality in some sense. So this term was coined officially by Witzenhausen in 1976. And I think more recently, there's a formal definition of it. Right. So this simplifies searches for the optimal or good control policies and yields algorithms. If you didn't have an information state type idea, what you would be doing is you'd be searching over policy spaces and over whole time, so you'll be searching over, the problem will be a very complicated problem. With an information state, what it allows is essentially allows you to decompose things in time. So essentially you can say, okay, all I've observed right now, I can compress it to something nice and see what happens in the future. And that gives us dynamic programming. Okay, so as an algorithmic flavor comes out because of this information state. And once you have that, you can also, in today's world, you would throw in reinforcement learning if you want to, or other learning-based solutions and algorithms. So an example of this is what you look at Markov decision processes. So I think part of Aditya's tutorial would have been on that. And there you have a Markov state. And what you know is that you can, my history is all the past states and past actions, but I can, without loss of generality, throw out everything and just concentrate on using the current state. I may need to use randomized policies, but I can still focus just on that state. So I'm actually taking a severe compression of the history, and still that doesn't hurt me. Okay. This is, actually should turn them around, but this is both model and strategy independent. Right? So essentially, so I don't need to worry about the model. I just know it's a Markov decision process. I don't need to know the transitions, or worry about the transitions. I can just focus on the current state. It's also strategy independent because independent of any strategy that you would have used, this compression works. So this is a core part of what comes in an information state. Strategy independence is an important thing. Sometimes in practice, if your Markov state is very large, then you have to do more. That's what is done in the function approximation literature for reinforcement learning. You are actually compressing it even further. And so that's a different, so that sometimes will be strategy dependent, but you're just looking at, I'm giving this as an example more than anything else. Now, if you go to partially observed Markov decision processes, you have this notion of a belief state or the nonlinear filter. which is another information state for the system. Unfortunately, this is strategy. Well, this is the nice thing is it's strategy independent. So this the belief state does not depend on what strategy you've used. That's why you can think of an alternate Markov decision process on just the belief state as being your Markov state, and then run your control based on that. Okay, so there's what is called sufficient. That's a sufficient statistic, and the control policies based on that will give you the optimal. Unfortunately, though, this is highly model dependent, and so it depends on both knowing the transition kernel as well as the observation kernel. And that's partly why reinforcement learning has been difficult in this problem. Of course, Aditya would have told you a lot about the developments that he's instrumented, and others have as well. So this problem does have a model and strategy independent information state, which is the entire history. That is obviously an information state always, but that increases in time. And the nice thing about the belief state is that domain of the belief state is fixed. Of course, you're now going from something that, if it's a finite state problem, you're going to distribution, so obviously you're increasing the complexity going that way. But nevertheless, the domain is fixed, and you could get time invariant behavior. So that's where you get the simplification, at least conceptually. So in some sense, I'll mention this. A critical problem that has been studied in a way is, what about information states in multi-agent teams? Multi-agent systems in general and in teams. And there's been a lot of progress on the teams part. So some of this talk will rely on that, and I'll mention it when it's appropriate. Okay. So coming back again to just the team setting, even in the team setting is very hard. Sure. Yeah.
So the optimal strategy, you have compressed this entire history to the current state in the MDP set.
Yes.
But you still need to know the model to be able to understand what actions in the future.
Yes. The planning. The compression is independent, right? So the fact that current state I'm working doesn't depend on knowing the model. Whereas when I do the POMDP, it does depend on that as well.
Compression.
Yeah, the compression is model. Yeah. So one of the core challenges, and this will come up in my talk everywhere, is information asymmetry. And it's also true in multi-agent in the cooperative setting, because each agent could potentially be working with just their private information. And what happens then is agents need to use complex reasoning to infer the other's private information when acting. Right? So I need to know why you're taking such a decision. Even though we are in the same team, if you do something, I have to know why you've taken it and sort of believe that you're doing the right thing. Right? And this essentially leads to what is called signaling, which you're looking at actions and inferring what is happening. So you're looking at the strategies and saying why the strategy is taken, and that's called signaling, and that really complicates how you would construct strategies in these problems. And the information asymmetry also leads to non-classical information structures. So the standard information structure is what you see in a Markov decision process, as in the controller has the information, all the information up to that point of time. Even in a partially observed Markov decision, it has all the information there. Whereas in this setting, you could have, there is no agent who may have all the information of the system at the time of taking action. So this is called a non-classical information structure. Okay. And that makes sequential decomposition, essentially the dynamic programming type thing, very hard. And that's what really is a challenging part of this setup. If you can characterize an information state, then you can get to sequential decomposition. So in some sense, that's a very, at least one well-charted way of approaching these problems is to come up with an information state and then work with it. In the learning context, the way this information asymmetry plays out, or is using the fact that if different agents are playing and learning at the same time, and so they're changing their policies, what every other agent faces is no longer a stationary environment, but it's like a non-stationary environment because everything, the whole transition kernel depends on the strategies of everyone. And so if everyone is changing, then the whole system keeps changing. Right? So the kind of things you would use in reinforcement learning typically would be harder to apply directly, at least. Nevertheless, teams are much simpler than games. And where it comes out is I don't need to worry about deviations that agents are, I don't have to guard against that. So essentially, in sort of technical speak, I don't have to worry about off-policy behavior. They're only on-policy. So anything that is sets of measure 0 don't actually bother me in this case. But I still have to worry about the complex reasoning that I form beliefs on you form beliefs on me, and then I need to know why, how you're forming those beliefs, and the hierarchy of beliefs have to still be adhered to. Yeah. So even if you include all of that, this is a complex problem. In general, it's NXP complete. And so that's from the complexity side. But if you look at even examples which you take the Gaussian type, linear Gaussian type systems, the Witzenhausen counterexample is a way to show how it just increases in complexity, where no longer, the optimal policies are no longer linear, but they are more nonlinear policies. And the search becomes incredibly hard. The other problem with these multi-agent problems, even the team settings, is we don't have benchmarks. Okay. Very few benchmarks exist. I mean, there is a benchmark like Hanabi, and I think that's one thing example as a game that you play. But in terms of algorithmically saying, okay, this is going to be the benchmark, you can test it, it's very few things exist. So my student, former student Deng Wang with his postdoc team, they have some algorithmic solutions which still solve more problems, but they're still very small. Okay, so that's, unlike the way you want to compare it to the Markov decision processes where you can essentially solve pretty much anything if you're okay. So with that being there's still solutions that exist for these team problems. And the ones are more conceptual, obviously, not algorithmic. And there are three sort of ways people have approached it. One is what's called the person-by-person approach. So if you have a common goal, it's easy to see that the team optimal solution is also an Nash equilibrium, because no one will deviate from that, because it's the... And so the person-by-person optimal essentially says, hey, I'm going to start looking for a Nash equilibrium type setting. And then if here actually the system guards align, then if there's some convexity or nice things or some potential game structure, then yes, what you would get to would be the team optimal solution. There is also another approach, which is the designer's approach, which is more an open loop approach. And that works on functional spaces. And that gives you a solution. I mean, the thing is, there are many solutions that exist to these problems, but the designer's approach is a very complicated function optimization problem. But there are problems for which the solutions exist using that, and I think one of them is in Aditya's thesis. The approach that I'm going to talk about more and use more is the common information approach. And this was pioneered by Nair, Mahajan, and Tenekitsis. And here you're going to use the common information that the agents have to sort of coordinate things. I will tell you a little bit more about this at a high level here and more descriptive much later on. So the common information approach transforms the problem. So it takes the given problem, transforms it to another one. It's a fictitious coordinators partially observed Markov decision process. Okay, so you're going to form an analogy between two problems and then show that if I solve it here, I can come back and find a solution on the other side. And part of it is it changes the actions that the coordinator has on this POMDP are going to be different. So what are called prescriptions. So this is going to be a partial function, and I'll go into more details when I talk about this, because part of the structural results will rely on this. And once you have that, this equivalence essentially what was established by Nair, Mahajan, and Tenekitsis is if you have deterministically chosen prescriptions, you can show that you can go back and forth between the team problem, the decentralized team problem, and this fictitious coordinated problem. And the way they can think of conceptually solving it, each agent instantiates the coordinator and solves the problem, and then plays out their part of the strategy. Okay. So this is at a very high level. So this actually provides an information state because they can go to this POMDP here and use the POMDP information state. And this gives you a strategy independent information state, but it's model dependent because it requires all knowing the transition kernels of every agent and the observation kernels if it's partially observed. So that should give you some background of where I'm going. And so I will start with sort of the problem that helped us think about this, what I'm going to present. And this is from a paper in Infocom in 2024. Think of the following problem. You have so it's a wireless problem. I have a base station. I have a bunch of edge devices. I'm looking at a video streaming. I'm streaming videos to the edge devices. So each one could be watching its own video, perhaps. Right? There is a transmission energy constraint at the base station. I mean, this is common. The edge devices play video packets and send some application level feedback back to the base station. I mean, this is another thing that is real systems. But these aren't fictitious systems, they're real systems. There's some feedback delay or some channel delay in which this information goes back to the base station. And so this is something that we had looked at when I was working at Motorola. So that was another thing. After my PhD, I worked at Motorola for a while. So competing with Rajesh, who was at Qualcomm at the same time. And so we did look at some problem like this, but decided I didn't know how to think of solving it at all. No structural insight, nothing. And so we abandoned, assumed there was no delay and everything was clearly visible, came up with some solution. And but the one thing I wanted to mention from that is this was assumed to be where this is a designed system that happens for most cellular systems. And so you could think of this as a team problem. You don't worry about the individual objectives of each. So you want to get the social welfare maximization, essentially. Right? So that's the common goal. And the base station would, so they are all operating such that the social welfare is maximized. So let me just give you a system model for this because I think that's very helpful. So think of n edge devices and one base station. It's a discrete time setting. So I have the edge devices have some state. So I'm assuming that these are finite valued. So this xn is the application state. Maybe it's the buffer, right? X2 is something that is some quality of experience tracking metric that you have. Say how many have been dropped, whatnot. And I can collectively collect all the states in this vector. Let's assume right now that the base station has an infinite buffer of all the video packets. I mean, that's reasonable at this time scale. And so you have an action at the base station. So the play out as the edge devices can play out a certain number of packets at any time. So VTN denotes that. Assume it's finite again. Collect all these actions together. The base station will decide how many packets to transmit to each device. So that's again some action. And what we assume here is the feedback says that I'm going to send my state to the base station, but the state arrives with some delay. The delay is it can be 0, but 0 is the easy case. You have a centralized system. Assume D is 1 and above. Right? And now the way the system works is, yes, I'm sending the feedback to the base station, but only the base station hears it. Right? So in this system, the base station gets feedback of all the edge devices with some delay. So there is no one agent that has this information of all the agents, right? So there is no common information to the system as well between agents. And this is a problematic. No, but this playout is also done here. So my buffer I could have, because I played out a lot, my buffer could be very small and I want more packets coming to me, for example.
But the playout is happening at a usual rate. The usual frame rate cannot be slowed down.
Well, if you have different rates, then you could be playing out at different rates, for example.
In embedded rates.
Yes, yeah. So I mean, right now it's still an abstracted problem. I mean, to make it a real solution, you have to do a lot more, of course. Yeah. So nevertheless, at this setup, I mean, this is still a very complicated problem, and it turns out our methodology, we're able to solve this to actually make it, I would say, scalable, and that's I'm not going to talk about this problem anymore, but I'm going to talk about the methodology and so on. But this was our sort of motivation to study this methodology. So
here, all the agents are sending all of the information that they have to the base station.
yes.
And all the decisions are made by the base station.
No, even they decide how much to play out as well. Yeah. So there are n+1 controllers in this setup. Yeah. So the formulation I'll be considering is a multi-agent constraint decentralized POMDP. This is the decentralized POMDP is an AI or machine learning term. Yeah. So I'm going to think of the system of n number of cooperative agents. Think of the edge devices plus the BTS here, who are taking action sequentially in discrete time. The environment has some internal state S that lives in some state space S. Okay, I'll talk about that more later on. After the agents have formed a joint action, so all the agents take their action. So AT is the collection of all the actions. The state of the system evolves to ST plus 1. Okay. And then the agents get observations. They get this joint observation. I'm going to denote 0 to n. I'll tell you what the 0 means. And the team incurs immediate costs. If in the learning context, it should be countable state space, but otherwise it's allowed to be general. In the planning case, it's just some function. Right? So C is going to be the immediate cost. This will be the primary objective that they're going for. And D will be constraints that come for the constraints. And D could be some k-dimensional vector. Now the observation that pulled out 0 is observed by all agents, so this is the common observation. And observation n, component n, is only observed by agent n. Okay. So they may not see the whole environment, they may see a part of the environment, whatever, this is all sort of encapsulated in this description. So this is sort of a cartoon for the same picture, but it's essentially the same thing here. So we allow the state space to be general topological space. So yes? Sure. This one? No, this is not the base station. This is just the abstract problem. So there's some internal, system, environmental state, right? Yeah. It could be unobservable. It could be, I mean, some agent may see the whole state. That's also allowed. I mean, so, and some agents may see part of the state. The state could have multiple components. You see some, all of that is, I mean, you allow, the generality allows for all of that. It's the common observation, yeah. O of 0 is the common observation. It will be, I mean, this would be common information here, yes, right. This observation could include actions and may not include actions as well. Right? So you may not get to see everyone's actions. You know your action, but you may not get to see everyone's action. All of that can be encoded in this abstract formulation. Okay, while the state space is general and topological, the observation state is assumed to be countable, and that's important. So if I was in a fully observed model, then obviously the state space also has to respect that. Yeah. The action spaces are going to be finite action spaces. At this moment, we cannot go beyond that. I think we may be able to compact. I'm not 100% sure. So the transition law is as follows. So my state space is in some general topological space. So given my current state space and the action vector, the probability that my next state lives in some Borel measurable subset B, and next observation is, since the observation is countable, I can take a look at the value that they have, is given by this transition count. In this problem, I need to specify the initial distribution as well. So it's some probability measure on S cross O. Okay. So having set that up, I'm going to now describe the optimization problem that you're going to work with. So before that, I need to tell you what the information structure is. So there is this common history. So everyone gets to see this O, so you can denote that as the common history, HO of T. Each agent has a private history as well. So assume that there is no intersection between the ON and OT, so O0, so this is just the private observations you're getting. You stack the private observations and the actions, assuming that the actions are not visible as well to others. And this becomes the private history of the agent. So let's assume, and for the simplicity, assume that even the actions are not visible, only something in O0 is what is there. So everything, only in O0 is in the common part, everything else is sort of separate from it. And that's the private history. So each agent, their policy is going to be of the following form. You can take a randomized action, so you take the common history plus the private history, concatenate that. Based on where you are, you choose an action, but you actually choose a distribution, and then based on that distribution, play out the action that results. Okay. So this would be what's called a behavioral strategy. Okay. So based on the history, you choose, this could be a pure strategy as well, in which you fix the distribution is choosing a point mass. But you could also have a distribution of the actions. So the policy profile space will be just the concatenation of all of this, a product of all of these. Okay? And little u will denote a typical member of capital U. So once again, I'm looking at behavioral strategies, so I'm allowing agents to randomize, but the randomization is based on the history they are currently, and then they take the action based on that. So once you do this, you can define a measure on the space. And this is the Kolmogorov extension theorem or Iona-Tulsia theorem, Ionescu-Tulsia theorem. Anyway, based on all of that, based on your profile and the transition kernel strategy profile, you can actually define an expected infinite horizon discounted cost objective. And similarly, you can define the vector of discounted constraint costs as well. What we will need for this work is actually not just consider U, but look at mixtures of U. So essentially, I'm going to be able to think of having a distribution on U, and I'm drawing one of these at random, profiles at random, under whatever measure that I have. And using that, construct the I'll tell you why that is important. That's going to be a crucial part of the whole thing. So the way this is done is you have to define a suitable topology on this policy profile and say that then you can define a set of probability measures on that, and everything works out. And then you can define mixing as this form. So I'm going to differentiate between mixing and behavioral strategies. So behavioral strategies, the randomization is done by each agent, right? Mixing is done, say, at time 0, essentially. I'm going to decide, hey, this is the profile that you use. Using that, you can now take, once you've defined this cost for every strategy profile, you can take an expectation over strategy profiles. Yes? So like in the example that I presented, the transmission power thing is a constraint. So if I say on the average, I cannot cross this level. So in a discounted cost setting, that would be an example of that. So once you do that, now I have a nice optimization problem. I want to minimize the cost. Now this is over these mixed policies, such that, yeah, so this is the constraint that I have. I'm allowing for the mixtures of behavioral policies, but I have to meet the following constraint, saying that the constraint cost is above, less than equal to some given threshold. Okay.
Can you explain the mixtures of behavioral policy? Can I take the action based on history and probabilistically?
Yeah, so what you do is, think of, yeah. So the simplest way to think about that would be to think of just having pure policies. So pure policies, there's no randomization done by any agent. So at time 0, there is a random variable that decides, okay, this is the policy that is profile that's going to be played. And then everyone plays that profile. Okay. Yeah. So, well, this is an important point. Yes. All right. So just for to make things nice, we'll set the C lower bar to be infinite if no feasible mixture exists. Okay.
Why do they use the notation hat there?
Well, because we went from behavioral policies to mixtures of behavioral policies. It was more to differentiate the two. There's an additional randomization that's ongoing. Yes. Okay, so once I have an optimization problem, I mean, everyone, the first thing you do is, hey, can I look at a Lagrangian relaxation? Because I have this constraint problem, I want to put it up in the objective, look at an unconstrained problem and try to solve it. So I have a Lagrange multiplier, lambda, which is k-dimensional, and then I absorb the constraint into the objective, and I have the Lagrangian. But the sort of question you should ask for any of these things is the Lagrangian formulation useful? In this case, you will, would you get, I mean, essentially the question of duality, whether it's weak duality or strong duality, that's the essential question. And the thing is, this is not an easy problem. So one of the issues with the problem that we have is this type of approach is the convexity approach that Borker pioneered and then Altman followed up in the Markov decision processes and constraint Markov decision processes framework. There's a very nice things simplify very well because you have these things called occupation measures. You can rewrite the problem in terms of occupation measures. We don't have that in this case. The general decentralized setting does not allow that. I'm right now playing with histories. You can think of I'm looking at distributions on histories and working with that. So this is a very complicated object that optimization problem that I'm working on. I could use the common information approach, but it needs technical innovations, and I'll come to that. In the generality that I posed, it will lead to an uncountable state space in terms of the, if I go to the belief-based constraint Markov decision processes. And those aren't very well understood from what I know. There may be some work now, but a lot of the nicest results need countable state space underlying there, and this is also work by Altman and Borker. Yeah. I think there are results that for these complicated objects, but I think it's still not yet to the level that I need for this. Yeah, go ahead. The hat is, I take behavioral policy, or take just pure policies, and I randomize over them at time 0. So in different sample realization, I'll be playing different policies, essentially. And I'm averaging across that. Time 0, yeah, for example. That's the simplest way to think about it. You can have behavioral policies also, so when each agent does his own randomization after that, but what is the strategy profile that's picked is time 0. Yeah. Yes. Yeah. So the original will have to be that's where it's going to be when the final result comes out, and sort of prefacing a little bit. What will turn out is if for these problems you'll have to do joint randomization. If you don't allow joint randomization, at least at the level of the mixing, you're not going to be able to solve them exactly. The strong duality doesn't hold in some sense. So the way you want to think of it, there is some common randomness that they can use to generate the strategy profile at time 0, and then each person plays it out. So that's the way you want to think about it.
Is there a connection to the correlated equilibrium?
Yes, it should be, yes. The correlated equilibrium is still so you should think of the correlated equilibrium as a generalization of the team optimum policy. Because there you're still looking at individual goals.
So this would be, you're thinking of the aligned objectives
Yes.
and correlated.
Yes. That's right. There's one difference though, the correlated equilibrium, and that'll come up much later on. Correlated equilibrium assumes a randomization device. Here I'm not going to assume a randomization device. And so that's a technical difference, and that's the difference that stochastic control and game theory seem to have. It'll come later on in the talks. Let me actually speed up a bit. So the assumption one here is this is very general assumptions. The objective cost is bounded from below. The immediate costs are going to be bounded from above and below because I don't want to have infinity minus infinity somewhere. And the third assumption will be Slater's condition. So there is some mixture policy that meets that constraint strictly. Okay. So under this, we have two results. The first one is strong duality. So you only need assumptions 1 and 2. So it just says that I can do the min-max, max-min is fine. So I can do so this is the Lagrangian. I could optimize over the Lagrange multiplier first and then over the policies or interchange them. And here, this is an unconstrained problem, so I would normally do that. Moreover, there exists an optimal policy such that it meets once I feed that policy and I optimize over the Lagrange multiplier, I will get the optimal cost. This does not say that there exists a Lagrange multiplier, and that needs the Slater's condition. Once that is there, then you get the saddle point theorem holds, and complementary slackness also holds. So just to give a very brief thing, the proof relies on, it's usually a min-max theorem, an extension of the standard ones. So that's sort of the first part. I know I went a little slower, but that's okay. So we studied this for infinite horizon discounted costs, multi-agent constrained decentralized POMDPs. The result I just mentioned was strong duality and existence of saddle point. This, as I mentioned, this holds over policy profiles, which are mixture on the mixture spaces, and you need joint mixing. You can actually come up with examples. We have in the thesis, there's an example. You can use an example from Altman's book to construct a multi-agent team where if you were doing individual randomizations, you will have a duality gap, whereas if you use a joint randomization, you will be able to meet a strong duality. Okay. As I mentioned, mixing is carried out at time 0, and this is needed to ensure tightness of the joint constraints. Okay. So in some sense, this is a good result because strong duality holds, but it's not very useful because it's still a very complicated setup. You would, as a practitioner, prefer to use behavioral policies. Yeah. And the other thing with mixing is, so I know in certain sample parts I'll meet the constraint, I'll exceed the constraint, I'm getting it through averaging. In certain problems, can I do better? It doesn't work for discounted cost, but in average cost that may be necessary. So getting to a behavioral policy is a better setup. And one of the things is how do you translate this? The other sort of characterization is, okay, I have this optimization problem. If you know the results in constrained Markov decision processes, you know that there is a behavioral policy, it's a randomized policy, which needs at most k number of randomizations to be up. That's a sort of characterization that Borker had. And actually it was, and others as well. Can you say something about that here? At this stage, the way I've written it, you cannot. And can you develop learning-based schemes using this formulation? That also you cannot at this point. So this is too complicated. And so the structural results are sort of taking it from this framework to make it more palatable in some sense. Okay. And the big challenge is there is no occupancy measure characterization. That's what really gives you a lot of the results in that context. So that's where the second part of the talk is. So before I get into that, I again want to go back a little bit and look at how agents interact with environments. So the agents use interaction mechanisms, we call these, to work with the environment. Let's just take a single agent setup. In there, things are quite common. We know several different ways that in single agent settings that work. So one is behavioral policy. So this one agent, there's no difference between common and private and history, they're all the same. Based on your history, you take a randomized action, right? That's the behavior. Pure policies are you just take one action, so it's no longer, the distribution is point masses. You have Markov policies where I decide I take the state, history, I just come up to the current state and I take those actions. I have stationary Markov policies where take a particular function of the state at any or all time. I don't worry about time per se. Okay. So these are in, if you go back and peel through the terminology, so this would be called perfect recall because I hold all my information that I have, I hold it and reuse that. These would be strategies which are called imperfect recall. So I'm dropping information, but this has something which is called not absent-minded. So I don't mix time. Right? I know where I am in time, whereas stationary policies are imperfect recall and they are absent-minded. I just mixed all my time. I don't care about where I am in some sense. Okay. So these are the terminologies that are there in decision making. And a lot of the basic courses in stochastic control sort of spend on, hey, decide to clear up this thing and say which are more relevant policies to consider and so on and so forth. Right? And you can consider several more. You can mix these. That will be randomization at time 0. You could mix behavioral policies, mix pure policies, so on and so forth. We clear through all that and say, okay, you can essentially in all the courses we say, oh, you can work with Markov policies or stationary policies and just stop there, right? So a few things that one needs to understand is imperfect recall versus recall, what are absent-mindedness and randomization. So the first thing is this randomization device. It's going to be very important. So in stochastic control, what is typically done is you have these policies, you construct the policy profile, you apply some sort of topology to that. If things are nice, then you can generate probability measures on that, and that's the way the randomization is generated. Okay. This doesn't work generally beyond countable state space settings. If you go, there are problems. And so in the game theory literature, this is coming back to Oman, you have a randomization device, so this is where the omega comes in from. And so your randomization is developed by this randomization device, and your policies are sort of measurable with respect to omega times the history, and you take actions based on that. We will be sticking to this, and this is sufficient for our purposes. The other aspect is memory. Now, these are the domains of decision rules. As I mentioned, perfect recall is based on decisions based on the entire observation history. Okay? Imperfect recall, the agent forgets part of our observation history. Okay? Now, there are special imperfect recall cases, the information state. I already mentioned that in the beginning. There, even though I'm throwing information out, I still do as well as knowing the perfect recall. Okay? But perfect recall is important because there is a famous result called Kuhn's theorem, which allows you to go between mixed strategies and behavioral strategies. And that only works under perfect recall. Okay. And now absent-mindedness, as I said, is an agent can choose a distinct rule for each, without absent-mindedness for each time step. With absent-mindedness, you can mix time. And sometimes you mix a few times. I mean, this can be very general, and we generally end up using stationary strategies because they're, again, very nice, simple to learn. Okay, once you have these distinctions, once you go to a multi-agent partially observed system, the table that I showed just explodes. So you have, I mean, just with perfect recall, you have a whole bunch of these strategies. You have decentralized behavioral policies. You have these coordination policies which I'll talk about. You can jointly mix them, you can individually mix them. It just completely explodes. And then once you add imperfect recall with no absent-mindedness or absent-mindedness, again, this whole thing. So part of what the exercise, I mean, we were working with things of this, in this setup here. I want to come up with something that is simpler, that allows me to then consider trying to solve it using, you say, algorithmic means, say computational means. Or approximately optimal also, I'm fine with that too, but I want it to be computationally possible. Okay. So a lot of what I'm going to talk about right now is this is the space in which I establish joint duality, strong duality. This is mixed behavioral policies. It will show that I can translate from there to pure mixtures of pure policies. I can look at mixtures of pure coordination policies. I haven't explained that yet. To go all the way down to behavioral coordination policies, I have to make one technical assumption under which you can make this loop. And then I can just focus on this side and develop my approximate information state-based ideas that Aditya might have talked about as well. Okay, so for that I need to explain this coordinated policies and coordinated system. So this is the common information approach, actually. So this is where I said I'll go into some detail about this. So think of a fictitious coordinator. These are different agents. The information to each. So what does the coordinator see? He just gets to see the common observations, but does not get to see the private observations of each agent. Right? So this is the common coordinator is only seeing what all agents see. Okay. The agents assumed in this problem are assumed to be passive. So the coordinator will tell them to do something. I mean, not do something. I'll tell you what that is. It's called a prescription. They will obey it. Okay, so in this problem, that's how it is. And these prescriptions will be denoted by gamma. Okay. What are these prescriptions? Okay. Now, these prescriptions are going to be functions. Essentially, what the prescription is going to be a big truth table. It says, hey, your current history is this. If the value is this, play this. If your value is this other one, play this. So I'm going to list the whole thing out and give it to you. So what I've done is I've sort of exploded the space to be much larger. I'm sending you a whole truth table as opposed to saying this. And you know your history, so whatever realization you have, you play the action corresponding to that. That's where you're being passive, and the coordinator never gets to see your private history, but he takes, based on the common history, gives you a prescription that you get. Okay. So this is an enforcing instruction. And once you formulate it this way, when you look at the coordinators problem, you have a single agent, and in this case, constraint partially observed Markov decision process. So you have taken a decentralized problem, constraint problem, and formed an analogy with a single agent problem. Okay, this is a fictitious problem, but still you can form the analogy. Conceptually, this is right. Okay? And if you allow perfect recall for the coordinator, so he remembers the previous prescription that was given, then this is a very standard single agent problem. And since it's partially observed, you can think of the information state is given, it's what you would do for a single agent partially observed Markov decision problem, form the belief state, appropriate belief state. So this is the core conceptual idea that was there in Iyer, Mahajan, and Theneketsis. Okay. And so once you have this, then you can think of, oops, sorry, I rushed through this, but that's fine. So you can do the same thing. Now I have the coordinator. I look at all the policies that the coordinator would have generated. So you have this essentially based on the history of the coordinator. You are producing these actions. And the actions are prescriptions, and this becomes a coordinator's behavioral policy, and this can be implemented by each agent. This is called the coordination policy. Okay. Again, I can randomize, so I can consider mixtures of these, and that would be the mixed coordination policy. Okay. So once you set that up, you can have behavioral coordination policies where the coordinator, based on his history, randomizes, or mixes at time 0 and then does the same thing, because now the single agent, you can consider it that way. And so we can write another optimization problem where you just look at the coordinators problem. I'm looking at mixtures of behavioral policies, and I have the same sort of objective, which I want to minimize, and I have a constraint thing. What we show is that, it's a little bit technical, that the two optimization problems, the decentralized one and this problem, are actually the same. The solution will be the same as well. And the core idea then is how do you take a solution from here and map it back to the solution from there. That's essentially the structural result of, if I may. Yes. Yeah. Yeah. Is this the class of policies change? No, a mixture of behavioral coordination policies. That was just decentralized policies. It was everyone was. So here I'm looking at the specific coordinator-based policies. I'm looking at a subclass of those policies. So that's what was changed essentially.
And where does mixing across time show? How does that differ from this?
So it'll turn out that you could have substituted pure policies also. Mixing at time 0 is actually more critical in some sense than But what we will show is that under one particular technical assumption, you could just look at behavioral policies. You don't need to look at these mixtures, but then you have to at every time do joint randomization based on history at the coordinator level, so which is fine. Just using common information, you do a joint randomization, which is fine.
And the thing that you just described doing the joint randomization, is that equivalent to this problem?
Yes, it will come out to be equivalent to that. Okay, so the way there's actually two proofs. We have a more stronger proof right now. What we show is that we take two classes of interaction mechanism, W and W prime. We say that W dominates W time for horizon T. If you give me a particular W, little W prime and W prime, there exists some other W and W such that you get lower cost, objective cost, and you also lower constraint cost. And if you can do this for everything in W as well, so they are equivalent at time T. Right? If the dominance holds both ways. And if it holds for all time horizons, then the dominance is W dominates W prime. They're equivalent if you can write the dominance both ways at all time. Okay. What we show in some sense is that the original problem they're looking at mixed behavioral strategies are equivalent to mixtures of pure strategies, equivalent to mixtures of pure coordinated policies, which are equivalent to mixtures of behavioral coordinated strategies are equivalent to behaviors of coordinated policies. So what I promised was going from here to here. The one assumption we need for the result is actually is here. With the same assumption on the costs were there, but we also need to have a finite number of common observations and prior. So instead of countable observations, then make it finite observations. Yes?
So after the coordinator, if that truth table initially,
Yes.
is it any additional randomization or
So the coordinator chooses the truth table in a randomized manner. That's what you want to think about it. That's the behavioral strategy. So I have the space of truth tables. I just pick one of them with some distribution. That's my action, so I can have a distribution on that. Yeah.
But then the agent actually
Just implements that. There's no additional randomization. The agent doesn't, he's just following what the coordinator tells them. Okay. Yes?
Is this also necessary condition for that equivalence? That equivalence should not always hold, right?
Yeah, this is the, so this.
So you show that under this assumption it holds, but is that also necessary?
So I don't know how to go beyond finite observations, because what happens is that, so now look at the truth table is essentially all functions, right, that maps history to actions, private history. If that's countably infinite, then my actions are uncountable. The number of functions become uncountable and no structure whatsoever. So I have no how to manage that. That's technically hard. So unfortunately, I have to have finite things there. But the original result still holds. The strong duality result holds. This characterization of showing the two problems are equivalent doesn't hold anymore. Or I don't know how to do it. Maybe that's a better way to put it. Yeah. There is some small movement there. I think Sardar Yüksel has been doing some things, and under certain assumptions you can make some progress. But I think it's quite challenging otherwise. Maybe you need a different approach from the common information to make it work as well. Okay, so just to overview the other results, I'll be finishing in about 2 minutes. So the coordinator's viewpoint actually gives us a single agent constraint Markov decision process on a countable state space for this assumption. So then you can apply Borka's result on the number of randomizations to show exactly at most k randomizations is needed. You can use that formulation if you want to develop a primary dual method, but it's impractical because again, it needs the model knowledge and complexity grows doubly exponential in time. What we prefer to do is develop this multi-agent approximate information state. This is still, I wouldn't say this is still a computational solution. I mean, it doesn't, so it allows us to generalize some past results that we had on developing an multi-agent approximate information state. And the approximations use imperfect recall, unfortunately. So what happens with imperfect recall is actually in these, the mixing versus behavioral is a big issue because mixed strategies can outperform behavioral strategies. And the reason for this is quite intricate. So, so behavioral strategies you randomize at any given time based on the history you are. Mixture actually is going to allow you to, mixing will allow you to sort of randomize across time. And that flexibility is what allows you to outperform behavioral strategies. And so this is a big issue when you go to imperfect recall in games, essentially. So you can develop some nice smoothness in the approximations. The approximation goes down to 0, you get the original solution, and so on and so forth. Yes?
So this is, there is a lot of different kinds of mixing possible. So you have to choose the right mixing to outperform the.
Yeah, so the way the result works is there are problems. I mean, for this class of behavioral policies, I can come up with a mixed strategy that can improve, to give you better performance.
Is this like an existence result, or are you describing how to mix, or?
Not in general. I mean, there are examples in some sense you could think of it. You can come up, you give me a thing, I can come up with a constructive example for that problem that, hey, the mixing is actually outperforming behavioral policies. And this comes up in games quite a bit. Actually, the economists have studied this quite a bit, where they actually have examples where this thing holds. So going from perfect recall to imperfect recall is always tricky. But imperfect recall is where we want to be because that's when the strategies are simple. Okay. So I'll skip this. This is just telling you how that was organized. So I simplify the strategy to this. These are the equivalences, and we'd like to operate on this side. Okay. So I'll just end with sort of the extension to dynamic games. Can any of this thing work? This is all based on my student Deng Wang's work. So 2 papers in dynamic games and applications, and part of it is thesis as well. For some models, model and strategy independent information states exist. Here, the equilibrium using strategies with compressed information exists. Sometimes all equilibrium payoff profiles can be preserved. These are, but in general, the domain grows with time. I cannot get a finite fixed domain type compression. What you can ask is, can I follow the same approach of taking the common information-based belief as a candidate information state because it has time invariant domain? The problem is it's model and strategy dependent, unlike in the team setting where it was strategy independent. So there's a big difference going from teams to games. And then what we show, there are examples where equilibrium may not exist. And even if equilibrium exists, sequential decomposition may not be possible because you may be using his information from the, or actually parameters from the past when you're taking some action, choosing your action. So in general, I believe dynamic games are still very challenging. With that, I end. Sorry. Thank you.
We can take some questions.
Yes. So we haven't explored that as much, but in that wireless problem, we were able to take the duality part and show another structural result where you could think of the base station as being n controllers on its own, each just working with its own edge device. And then you just, so that was sort of a simplification of the structure you could get. We didn't look at it necessarily with the cost functions per se, but this was more structural insight of that kind, yes. But yes, there is a lot to be done in terms of trying those kind of things. But in general, if you look at partially observed systems, even there, I think the results that we know in terms of the structure of whether it's a threshold type policy or not, is still very limited from what I know. At least whatever is there is in Krishnamurthy's book, as far as I know. Beyond that, I don't know if anything else is there.
There are some situations where you can order the information structure.
Yeah, and then
you can still deal with it.
Yes.
I recollect Blackwell ordering as one of the ways in which
Yes.
more informative ones, the less informative ones don't know. So
Yes.
still non-classical, but still.
Yeah, so there's the partially nested, so those are things that work, actually, that's correct. And those are simpler. Partially nested, and nested is simple, you just have essentially, there's one agent who sees everything, so he can solve the problem and tell everyone what to do. Partially nested is, there is some, but those can be solved, and some, at least we know conceptually how to solve them. Algorithmically, they could still be very hard. Yes, there's a lot of, in the control, stochastic controls, they have looked at a lot of these things. There are complicated information structures called Yoshikawa as an S and T information structure where a lot of simplifications happen. Sometimes hierarchical structures are easier to handle as well. Yeah, the single agent class, they have been looked at. They haven't actually, they weren't looked at much in the multi-agent context, so we are sort of one of the few people to have looked at it recently. There's also some people in the AI side who have been looking at it as well, RL and AI side.
Yeah. Thank you, Professor, for an interesting talk.
Thank you.
We have arranged some refreshments. Please continue the discussions at Coffee Hut.